Initially, to start with, I would like to take few minutes to introduce about our company. It is the company started by Sridhar Balram sir in the year 2012. It is now it is having a strategic collaboration with the DMG Mori, which is an investing partner in AM business. And we started our company as a service-based company. We cater to various industries like aerospace, space, automotive, general engineering, tooling, medical and dental in India and abroad. We are the first metal 3D printer company launched in India, supported with AM Automate software for parameter optimization and property prediction. And we have developed our in-house software called AM Builder, which is for data preparation and process optimization. And all mission-related accessories also developed by ourselves only. Then coming to the Intech growth, this is a company founded in 2012 with 30 plus years of experience in foundry and machining. Started as a first AM service bureau in India. Later, we full-fledged entered into providing services from the year 2014 to 2018. We supplied many components to many government organizations as well. In the year 2018, we launched our first product called AM Automate, which is a parameter optimization software, which helps in developing the process parameters in a very quick time. Then in the year 2019, we have launched the software called AM Builder, which is a data preparation software, which helps in preparing the data for 3D printing parts. And in the year 2020, we launched a mission called iFusion SF1. This is the India's first laser powder bed fusion mission, launched and commercialized as well in India. Then in the year 2021, we have successfully installed seven missions, 5 in India and 2 abroad, 1 in Germany and one in Greece. Coming to Intech product portfolio, we manufacture iFusion series missions. It is of 3 categories. One is small format mission, mid format and large format. Small format missions will have a build volume of 150 mm dia and 180 mm height. Mid format is having the range 325 mm cube, and large format is having a build volume of 450 mm cube. And these missions are supported by as I mentioned, supported by softwares called AM Builder and AM Automate. AM Builder is for data preparation and AM Automate is for parameter optimization, that is process optimization. And end-to-end solutions is something which is Intech is providing to its customers and the people who wants to start their business in additive manufacturing. The process starts with design and DFAM. We have a strong design team internally, which will help in converting the conventional models to 3D printable models. In this process, like first we will take the CAD model, the conventional process, and we apply some design guidelines, that is DFAM, design for additive manufacturing. By applying those guidelines to the conventional parts, we will convert the part into 3D printable part with improved performance. In this process, we will do topology optimization, generative design, part consolidation, a lattice structure to reduce the weight of the component and to save the material. And once the design part is finished, then the selection of material will happen. In this process, like as of now, there are very few materials available for metal additive manufacturing. So then due to this, the selection of material is a very important criteria. First, we will analyze the material, what is being used for conventionally. Then by taking the property values, we will match the nearest material which is available for 3D printing. And also we will also try to replicate the same material with the same properties, like we producing, getting the powder of the same chemical composition. In the end of the my talk, I will be speaking on the case study what we have done. So here we will procure the powder, we'll do the characterization, we'll develop the powder, and we will qualify the powder. And then once powder is qualified, then it will go to the printing level. with the help of our missions iFusion SF1 and LF1, which is supported by the softwares for data preparation and the parameter optimization. Finally, printing will happen. Once printing is done, post-processing in this step, heat treatment is first thing for relieving and also to get the final properties. Heat treatment is very important. Then surface optimization based on the surface toughness requirement, some post-processing operations will be performed on the component. Then finally, to meet the dimensional requirement, machining will be happening, and finally the inspection and certification will happen. And our main target is low volume production. The adoption of additive manufacturing is limited because of the cost. If you can reduce the cost, the adoption will be more. So with the help of our software called AM Optomet, which is a parameter optimization software, the time required for developing the process parameters is very less using this software. With this, the overall cost for the development can be reduced, and faster builds, like using this software we can produce the process parameters which can help us in getting good productivity. If productivity is increased and the cost comes down, uh, and the mission, the overall build value increases, then obviously the overall cost per part will reduce. By this, low value production is very much possible. And material diversity in this, like not only the available materials for additive manufacturing, we always look to develop new materials as per the requirement from the customers. And also, like if you take for high end applications where high strength and high temperature corrosion and oxidation related applications, very few materials are available for additive manufacturing. In this case, first our DFAM department is identifying the right components for additive manufacturing and its working conditions and material what is being used until now, and that material we'll try to procure in the powder form and develop the process for it. And finally, batch production is something which we are looking at, like printing multiple components in a single build and reduce the cost. And coming to the technical discussion for today, today I'm going to speak on introduction to additive manufacturing. I will not spend much time on this sort of introduction, and quickly I will jump into the factors influencing the end process and the procedure for developing the process parameters. Introduction to additive manufacturing, then types of additive manufacturing. Specifically, I will speak on laser powder bed fusion process, which is also called selective laser melting process. Then AM process workflow, then AM design rules and guidelines, and factors influencing the AM process, strategies in laser powder bed fusion process, and material parameter development and qualification. What is additive manufacturing? You all may be knowing about what is additive manufacturing. I will say complete in a few seconds. The official definition of additive manufacturing by ASTM is a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. What it means is, in conventionally manufacturing method, if you want to produce a component, we have to take a billet and we need to apply turning, milling, drilling, all these operations to get the final component. It is called subtractive manufacturing. We are subtracting the material from the billet and getting the final component. In this way, there is a lot of wastage of material. Whereas in additive manufacturing, it's a layer by layer printing. Like the given component is cut into sections, many sections, and each section is printed at a time, and final component is produced. In this way, we are saving lot of material, and the complex features which is not possible in conventional methods can be produced in 3D printing. Typically, AM processes are classified into 7 categories. They are material extrusion, vat polymerization, binder jetting, material jetting, sheet lamination, direct energy deposition, and powder bed fusion. Under powder bed fusion, there are again 2 processes will come, which is laser based and electron based. We are into laser based additive manufacturing. The principle of working of laser powder bed fusion process is the melting of the powder will happen with the help of laser beam. During the laser sintering process, a layer of metal powder is solidified by heating the metal powder to a temperature above the melting point by exposure with the laser beam, and subsequent solidification will happen at the inner atmosphere. The atmosphere is very important in order to prevent the powder from oxidation. And once one layer is completed, the build platform will move down by thickness equivalent to the layer thickness, and with the help of recorder, the next a powder for the next layer will be spread onto the build platform, and as per the CAD model, and with the help of scanner and laser selectively, the sintering will happen, sintering and solidification will happen, and this process will repeat layer on layer till the final layer gets over and we will get the solidified part out. And this is the typical schematic of laser powder fusion process. Here you can see left side is for powder supply. It is a two-way powder supply thing, like from left to right and from right to left. A powder supply thing. Between it is a build platform where you can see the printing of the component is happening with the help of laser and focusing lens and moving mirrors called scanner mirrors. We are directing the laser beam onto the powder bed selectively as per the CAD model, which area needs to be printed, which area is not to be printed. All these details will be provided to this system, and accordingly the laser beam is directed onto the powder bed and selectively sintering will happen. Steps involved in laser powder bed fusion process. Here you can see top left side image, powder is there in the powder tank, then building platform, and after recoating, a layer of powder will be spread onto the building platform, then sintering will happen selectively, and in the image 4, again this process repeats, and you can see how the build platform is going down and how the powder tank is moving up. And in the image 6 you can see the component printed, how it looks. And to print the actual component, we need some supporting plate at the bottom. On top of that only the actual part printing will happen, that is called base plate. The size of the base plate will vary from machine to machine. Then printing will happen. Then once printing is done, we need to separate the printed components from the base plate. Then that is called wire cutting. We will cut with the help of wire EDM, we will separate the components from the base plate, and the base plate will be machined the leftover regions, and the base plate will be reused. Since we are cutting it, we can't direct cut the actual component, so some clearance we need to provide from the base plate to the actual component start. That is called wire cutting clearance. It is normally 1 to 2 mm will be provided for any component that needs to be printed. I'll just play a video on how the laser powder bed fusion process looks. This is how the process prints. And coming to the process flow, it has 3 phases. One is design, manufacturing, testing, and qualification. In the design stage, first the specifications, what is required for designing a component will be taken, and with the help of the CAD softwares, as per the specifications, it will be designed. The input for data preparation in additive manufacturing is STL file format. So the CAD model will be converted into STL file format, and the STL file will be inputted to data preparation software, which we are using is AM Builder. We'll import the part and do all the orientation and support optimization things in that this builder software. Then finally, once that is done, then slicing, like it is a layer on layer process. We need to slice the component into number of layers, and the data, it is called INSL. A file is transferred to the machine, and as per the data which is provided in the INSL, the building of the parts will happen. Once printing is done, then it will be removed from the machine. That is called part removal. Once part is removed, then post processing we need to perform. Once post processing is done, final thing is that part inspection. If the specifications are within the limit, the part will be accepted. If it is out of the specification limit, will reject and go back to the mission setup and check what is the problem. It is because of process parameters or any other process related problems, and we need to encounter that. Comes to the data preparation workflow. First, we will create the build of certain dimensions of the mission. Then we'll import the parts. If any errors in the STL is there, that we need to fix it. Then there are certain limitations in additive manufacturing called thickness. That is that is called minimum thickness. That is only possible in the process. For that, we need to check wall thickness analysis. Once all the things are satisfied, then we need to position the component on the build platform. That is called the orientation. Which orientation will give less support? Since supports in this process is the best, we need to orient in such a way that the support structures are less and the build time is less, in order to improve the productivity. Then once that is done, then we need to do distortion analysis for the support which we are given, whether it is okay that part is printable or not. If you given less amount of support, there is a chances that the distortion will happen, because this is a process where melting is happening. There obviously thermal stresses will be induced in the component, due to which there is a chance of distortion. So this distortion analysis we need to perform. Once it is done, we need to slice the component and we need to export the data to the machine. You can stop me when you get some doubts in between while I give the presentation. I will play one more video on the process of laser powder bed fusion process. This is our Intech's SF1 mission, I fusion SF1. It is having a dimension of 150 mm dia and 180 mm height. This AM automate software for parameter optimization. Like initially, we can select the chemistry of the material and give the percentages to it. And if you calculate, if you click on the calculate button and if you adjust it, we will get the process parameters directly. We don't need to go through the DOE designing of experiments. We can directly get the process parameters. And with the help of AM Builder software, we can create the build size as per the mission and import the component and apply the hatching parameters. And this is the path generation. You can see the vectors are like for the laser movement. Once that is done, the file is exported into the mission. With the help of recorder, we are spreading the powder, and as per the sliced layer thing, we will be printing, and this process repeats till the final component is done. Why laser powder bed fusion process? I'll give a small comparison among different processes to produce a net shape mission part, assume it is having a weight of 61 grams. if you see on the left hand side. To get that, first with the billet, we required around 625 grams, whereas if you go for forging process, it is 211 grams. Wire DED 140, casting 120, joule printing 94, whereas in powder coat fusion process, it is 80 grams. Like almost net near chef we can achieve in this process, so that material wastage is limited. These are the few components which we have printed using laser powder bed fusion process. One is the flame tube. It is having a dimension of 600 mm and 300 mm height. It is sectioned into five segments and printed, and finally laser welded. And second thing is IN 700 turbine blades, which is having a dia of 100 mm and 60 mm height, and finally heat treated as per AMS 5660 to get the required part properties. And this is the impeller, the right hand side, which is made of 74 pH material. It has a diameter of 280 mm and 50 mm height. Machined and heat treated as per H900 cycle. Like in 3D printing, we will not get the mission surface which is seen in the image, so it has to be machined or post processed based on the surface roughness required. And these are the NGV blades made of CM247LC material, and finally vibro polished to get the smooth roughness. And this is one of the example for low volume production, like complete area on the build platform is utilized of the size of 300 cross 300 mm. Now I'll speak on factors influencing laser powder bed fusion process. Majorly the process is influenced by these categories. One is material, equipment, and production process, post processing, inspection of the component, and material qualification. When it comes to material, in this process, the input material is powder. So at the powder stage, all these major elements like chemical composition, tab density, morphology, flowability, particle size distribution, and the number of times the powder has been used. All these details you need to take, analyze, and once it is okay, then we need to go to the equipment level. There we need to check the calibration of the equipment and standard operating procedures of the mission and preventive maintenance checklist. All this we need to check. Once the equipment level it is passed, then we need to go for production. If it is needs to be, if DFAM needs to be performed the component, it needs to be performed. Inert gas flow. In this process, having inert atmosphere is very important. That conditions we need to check. Part preparation, process parameters. Once production of the component is done and it will come to post processing, first is stress relieving to relieve the stresses which is produced during the process. Then we need to remove the support structures of the component, then do the machining as per the requirement to achieve the final dimensions. Any surface roughness requirements is there, we need to perform those operations. Then once it is done, we need to inspect the component for visual inspection for visual defects, dimensions, and non-destructive testing, like to identify subsurface defects. Then finally, to qualify a component along with the actual component, or by printing one actual component as a sacrificial component, we need to take a few samples for tensile impact testing, or few portion of the actual component at test plot for characterizing and qualifying by measuring these elements like density, hardness, microstructure, and porosity. What are the typical problems what we face in laser powder bed fusion process? In the image here, you can see how a part is getting delaminated from the base plate. The reasons behind the delamination and the major problems which we get in the process are delamination of the layers, shrinkage, cracks in the part, distortion, and warpage during post processing. The reason behind this is maybe the process parameters, maybe a bad mission preparation, and maybe the base plate is selection of base plate is not suitable for the given material. There are many factors involved why the part is fail. How to avoid that? These problems can be minimized or avoided by sharpening the parts to relieve stresses. Like if a base plate is too surface is too smooth, then the weldability will be weak. So in order to that, having a little rough surface on the base plate will always help for proper bonding up first layer with the base plate. If first layer with the base plate is proper, then there will be proper heat transfer, dissipation from the printed layer to the base plate. So a kind of short pinning or every roughing is required. Then heat treatment to relieve the stresses before we actually break the supports. Supports is supporting structures. If that is without relieving the stresses, if you remove it, once the supports are removed, there will be a chance of distortion in the component. This needs to be minimized or eliminated. To eliminate that, we need to relieve the stresses. And one more important factor is shrinkage. Like during melting, you can see the image thermal expansion will happen, and during solidification, thermal shrinkage will happen. Due to this, final dimensions wise, dimensionally, there will be some difference during the printing and after solidification. So this shrinkage allowances we need to compensate in order to get the dimensional dimensionally accepted. To get that, we need to perform fine tuning thing, like how much shrinkage will be there for each material in x direction, y direction, and laser beam offsetting. All this we need to perform. We will have a standard uh, component for that. We'll print on that, get the differences, and by having the differences, we will apply the correcting factors. Here in this image, you can see on the right side laser beam which is the black color, and diameter of effective laser beam. That is because laser is a heat source, it has some curing zone around the laser beam. That means if you have a laser spot die of 100 micron, the actual melting will happen for 150 microns. In this case, when you are printing the surface of the component, since this is extra portion is printing, the part dimensions will come more. In order to reduce, we need to shift the laser inside the actual component by the distance equivalent to half the diameter of the effective laser beam. That is our experiment. With this experiment, we will get that beam object value as well. And support structures. And if support structures are too strong, there is a difficulty in removing the supports. Supports needs to be removed easily, and it should not be too weak such that during printing only we will get a problem with the delamination. So sufficient amount of supports and parameters needs to be selected in such a way that it has sufficient strength also to support the actual component. This will help in reduce the thermal distortion that led to cracking, curling, delamination, and shrinkage. One more important factor which is influencing the process is inert gas flow. Because in this process we are melting the component, and the heat process is boiling point, and then the vapors will generate in the process. And during the laser beam interaction with the powder, there is a chance that a few particles from the molten pool will get spattered from the molten pool. All this in the form of condensate. If it is falls back on the powder, which you can see the black particles are falling back onto the powder bed. If this is not removed properly, the powder will get contaminated. Like the life period of the powder will get reduced. If it is properly removed with the help of inert gas, then the quality of the powder will be there for a long time, and it can be used for many builds. Typically, nitrogen or argon gas will be used as inert gas. And conditions at which the operation is happening is also very much important, because the laser and the scanner mirrors will always be maintained at certain temperature, because The small deviation there will affect the part geometries, and all those problems will come into picture. So the typical temperature which needs to be maintained is 18 to 22 degrees and relative humidity of 40 to 60%. And most important thing is powder quality. Like if input material has some problems, then obviously the final component will have the problems. So powder quality needs to be evaluated thoroughly. In this case, we need to be checking morphology, composition, physical behavior. Under morphology, shape, size and shape. Size is nothing but particle size distribution, and shape is like whether it is spherical, satellite kind of things, or irregular shape. All those we need to evaluate. And comes to the composition, chemical composition, like each element is within the normal composition or not. Then microstructurally, like phase and porosity. If the porosity is there in the input powder itself means then there is a high chances of getting porosity in the final component. Then physical behavior, flowability. Here we are spreading the powder on the powder bed. So the powder is good enough to spread good onto the powder that is building platform. So flowability we need to check, and the tab density, like how good the packing of the powder is happening for a given layer. Like for a given layer, if it is a loose powder and less amount of powder occupies the build platform, then to get a good density, it is not possible. So tab density also should be maintained properly so that we will get the good density powder. And the powder needs to be stored in a good, tight, air-free containers, because if it is open to the atmosphere, there is a chance of the powder catches the moisture that is present in the air. So it needs to be packed properly and kept in a shelf so that the life of the powder usage can be increased. And before I start the procedure and why process parameters are important, I will show defects and the reasons behind the defects in laser powder bed fusion process. Before starting the defects in laser powder bed fusion process, I would like to take 2 to 3 minutes for the question and answers.
Sir, you talked about some structure support.
Yes, support structures. Yes.
Yeah. So after doing the process, what is the solution to remove these support structures? What solution is utilized?
No. This is metal based. Here we will not use any solution. It is manually. We need to use tools, pliers, all those to remove it. If support structure is too strong, then we need to do machining. Those things I will cover in the post process. It is yet to come. I will show how manually it is removed and how the machining will happen.
Okay. Thank you, sir.
Any other questions from the audience?
Sir, what is the minimum dimension that we can print with the equipment?
It also, we need to see the aspect ratio also. Considering all that, a minimum wall thickness of 0.3 is possible, sir. If it is 0.2 is also possible, but not for the bigger heights like 30, 40, 50 mm and not possible. If the height is till 10 mm only, 0.2 is also possible. But it is recommended to have 0.4 mm wall thickness all the time.
Minimum 0.4.
0.4. Less than is also possible, but it depends on the aspect ratio. Like how much height we need to print with that particular thickness. With 0.4 mm, it is possible to print whatever it is.
So 400 micron is the minimum.
Yes, sir.
Okay.
Any other questions?
Sudarshan, one question from me.
Yes,
K7. So what is the spot size you use? What is, do you use any range of spot size or a fixed spot size?
Like we are using fixed spot size, but it can be varied as per the requirement from the user.
Okay, so
We typically use 80 to 100 microns.
okay, 80 to 100.
Yes.
All right. And who is your material supplier?
We
You
have
get
many
the import.
suppliers actually. In India, Indomim is the company which is located in Kolhapur. They are supplying, but now they will not supply all the powders like aluminum and titanium based. Still, we are importing. Nobody is providing. For steels, nickel based and cobalt based alloys, most of the materials they are supplying Indomim.
Okay. Even they are supplying nickel-based material.
Nickel based, that's again depends. Like few nickel based, their furnace is not capable to produce.
Yes, yes. Okay,
It's
so I think there is no more questions. You can please continue.
okay, sir. Defects in laser powder bed fusion process. There are several reasons behind why defects in metal AM process comes. A variety of defects which may be initiated during the process can compromise the repeatability, precision, and resulting mechanical properties of the final component. One approach that has been used to control the process is by detecting, avoiding, or eliminating defects is process monitoring. This is called in situ process monitoring. During the printing only, we will use with the help of photodiodes or high-end cameras. We will be capturing the images or capturing the abnormalities, what is coming during printing, and we'll find the solution for it. And other reasons may be like improper powder doses, like if you are not coating the powder properly, or data preparation when support structures are not good, may leads to part failure. The one important defect is lack of fusion. Lack of fusion means unmelted zones in the actual component. If you see in the image, you can see the black zones. In that zones, the material is not printed because there may be like insufficient powder coated, or the parameters which we have selected is strong. The reasons for lack of fusion may be non-uniform powder coating, bad process parameters, improve inert gas flow. How to solve this? We need to optimize the process parameters. Very good in such a way that sufficient amount of energy we are providing to melt and solidify the powder. And second thing is porosity. Porosity also reasons behind is bad process parameters and improper inert gas flow. Bad process parameters is a direct thing. Improper inert gas flow, as I mentioned, the condensate which is generating, if it falls back onto the powder bed, it will disturb the laser beam. When the laser beam interacts with the powder, if this condensate is there, the penetration of the laser beam to the required depth will not be, it will not happen. Because of this, the porosity may come. So again, by optimizing the process parameters and by controlling the inert gas flow, the porosity can be controlled. And ball formation. This will happen when high energy density, high energy of the laser is used. This again can be solved by optimizing the process parameters. And work pace. This is the lift off on the base plate. This also because of bad process parameters, design, and the material. How to solve the issues? Again, we have to optimize the process parameters. We have to do DFAM, design product to manufacturing, optimize it, support based on material. This is support for failure. The support got delaminated from the surface. This is because of bad support parameters, support selection. So we need to optimize the support parameters as well while optimizing the parameters. Right selection of supports for the given location. Based on the location and the amount of component that area that needs to be printed on the support, we need to select the support. I will show like what are the different categories of process parameters that are important for building the component in the later slides. Then overburnt zones, you can see in the downside, it is burnt too much because it is downskin area and support is not provided in that area. And this is the overburnt zones because of bad process parameters and support not provided. How to solve the issue is providing the supports wherever required and the parameter optimization. And this in this slide is a crack formation. This is because the material may also be prone to crack sometimes. In those cases, we need to like optimize the process parameters properly, and we need to check material weldability. Only weldable materials only processed by additive manufacturing. And the atmosphere, what we are using, the chamber needs to be checked. And how to solve the issue is we need to optimize the process parameters, controlling the build atmosphere. And if material itself is prone to cracking, then we may need to modify the chemical composition without affecting the final properties. And what are the important process parameters that needs to be optimized? One is laser power, scan speed, hatch spacing, and layer thickness. Laser power is the amount of heat generated by laser in joules per second. Scan speed is the speed at which we are making the laser beam move on the powder bed. Hatch spacing is the distance between two consecutive laser beam paths in a given layer to cover the entire area. Laser has to go in vector forms. In the video, we have seen vectors are there. Each vector, the distance between two vectors is nothing but hatch spacing. Layer thickness is the thickness of each layer. Here I will be showing what is hatch spacing. Here hatch lines you can see, and hatch distance is between like two scan paths. Between that, what is the distance that is called hatch distance, and laser and the spot with what speed it is going is the scan speed, and the power is the direct is the amount of heat we are inputting. Layer thickness is also thickness of the layer. And here you can see contour lines without beam offset on the left side. That is that if the diameter is exactly sitting on the border of the component, half of the portion has come outside it. That is called dimensional error. As I mentioned, we need to put that dia inside so that we have to compensate the dimensional error. That is called beam offset. On top of that, you can see the beam offset. So that beam offset, whatever it is there, that much distance we have to move the laser beam inside the actual contour of the component, so that we'll get the dimensionally good thing. If the hatch distance is not maintained properly, there won't be proper overlapping between the two consecutive like passes. If that is not happening, lack of fusion will get. Two things which we need to keep in mind is, one is between two consecutive passes there should be proper overlapping, and between two consecutive layers, this is within the layer, this is between the layers. One layer should the present layer should get properly welded to the previous layer. If this is not happening, also in vertical section we'll get the porosity. Within the layer, if this hatch distance is not proper, here also we can see the lack of fusion. So these four are the key process parameters which we need to optimize to get a good quality, a good density component. How to decide these four process parameters? This is depending on energy density. Energy density is in terms of joule per mm cube. It is the amount of energy required to melt a material of 1 mm cube. Like to melt a 1 mm cube block, how much energy we need to supply. That calculation, I will give some guidelines how to arrive at the energy density. This energy density, once we arrive at the energy density, we have to split that energy density into process parameters. What is that process parameters is laser power, scan speed, hatch spacing, and layer thickness. Energy density is nothing but laser power divided by scan speed into hatch spacing into layer thickness. How to arrive at the energy density? For a given material, the amount of energy required for the melting 1 mm cube area is to be calculated. And this energy density varies from material to material because the material properties are completely different. If it is aluminum, the melting point is very less. If it is steel, it is more. Like if it is refractive metals, it is still more. So obviously the amount of energy required to melt 1 mm³ area is different. So first, for a given material, we need to collect all the material properties like density of the material, thermal conductivity, latent heat, melting point. All those we need to collect, and using some formulas, we need to calculate what is the amount of energy required to melt that. Once that is done, and we are using laser source here, it has certain wavelength called normally the wavelength which we are using is 1064 microns. At that micron, at that wavelength, whatever the energy we give for a given material, it will not consume all the energy, like because of the wavelength, like the absorption will not be 100%. The absorption factors also needs to be calculated when you decide energy density, like whatever energy density you have measured, if the laser or whatever it gives inputs, if it takes 100%, like your calculation, whatever by calculation whatever energy density you have got, you can directly use. But there are a lot of losses when laser interacts with the material, so that all losses also we need to consider. For example, stainless steel absorptivity to laser is 0.3 to 0.4. That means 60 to 70% of the energy which we input for stainless steel is going waste only. Only 30% only it is taking it. So whatever energy density you calculated, so for a given power, it is only 30%. Like that means you are giving 100 watts, only 30 watts is useful. So if the requirement is 150 watts, then 30 into 5, it's almost like 500 watts you have to use if the requirement is 150 watts. So for if you take aluminum, it is only 5 to 10%. Means that is 90% of the input power will get wasted. So the laser absorption factors for a given material we need to take into account. In that ratio, we need to multiply the energy density required, and finally we have to optimize the process parameters. For a given component, there will be exposure areas like core of the component, upskin, downskin, contour, and support. The key process parameters are 4 only, that is power, speed, hash spacing, layer thickness. But when a given component is given, it's there, it has 5 zones, that is core of the component, which is inside the component. Upskin, you can see, like when it is split into layers, bottom layer is downskin, that is since nothing is there underneath. On the top of that, core is printed, and if you see on the right side, upskin is there. It is a comparison between 2 layers, like core and core, bottom core and top core. If you see, whatever the area which is not there replicating in the present layer, that is called upskin. And if you see the third core area on the left hand side, it is a overhang compared to the previous layer. It is overhang, no material is there in the below layer, that is called downskin. So downskin parameters are different, upskin parameters are different, core parameters are different, and support parameters are different. And to get the roughness, border printing is there, that is called contour printing, that parameters are different. And if you go specifically, core again has like scan, stripe width, stripe overlap, minimum vector length, merge vector length. These all are required to get a dimensionally good and defect free. But basically these 4 parameters are very important. All others are also important, but if these 4 parameters are optimized properly, we'll get a good density things. All other things are easy to optimize. In a similar way, downskin has many process parameters, upskin has many. Contour and support will have all these parameters. When you want to produce a component with the goods with the defect free, this number of process parameters we need to optimize. It's almost like 100 to 150 number of process parameters we need to optimize. Out of all these, the 4 parameters, power, speed, air spacing, and layer thickness, are very important. Is about how we need to arrive at energy density and how the process parameters we need to optimize. Then comes to post processing. Why post processing is required? This is to remove the printed component from the base plate, removing the powder from the printed component, improving the surface roughness, improving the mechanical properties, reduce the residual stresses, and to achieve the dimensional accuracy. Here you can see how the printed component is removed. Once the component is printed on the base plate, it needs to be removed from the machine. And methods of removing is manual or automatic. Then we need to do stress relieving. Once the part is printed, in order to relieve the stresses, we need to put into the furnace, and based on the material, the heat treatment cycle, we need to select and relieve the stresses. And once that is done, we need to remove that component from the base plate with the help of wire cutting. Support removal. One of you has asked how supports are removed. You can see the image. Whatever supports is there, manually using the tools, we can remove like this. And its support structure is very strong, and with the help of building or turning, and based on the kind of operation which needs to be performed, we can remove those supports. And to go get a good surface finishing, we can go for glass fading, short pinning, sandblasting, vibro polishing, and electro polishing. These are all operations based on the surface roughness requirement. We can go through any of these polishing techniques. This is the final heat treatment. Earlier is the stress relieving. This is the final heat treatment to get the mechanical property requirement. For supervised solutionizing and haze hardening, it is something which we normally follow. During the solutionizing stage, we can get the homogeneous microstructure. Then by doing haze hardening, also called precipitation hardening, we can improve the mechanical properties. Materials for laser powder fusion process. Materials are categorized into 2 things. One is non-flammable and flammable. The category A is metal board, includes SS, maritime steel 625718, cobalt chrome, and 74 pH. Category B metal powders are LS at 10 mg and Ti6. To qualify a given material, we need to what and all the components we need to print. Basically, density and the microstructure coupons, which we can see in the left side image. Test blocks for density and microstructure we need to print, and horizontal and vertical tensile bars, and horizontal and vertical impact bars we need to print. And you can see on the right side image angular plates, like to get roughness optimization, we need to print those kind of parts. And this impact and these tensile bars are in terms of cylinders or in terms of cuboid structures. This needs to be machined as per the standards like ASTM E8 for tensile and E23 for impact. To the dimensions we need to machine and test it and qualify it. Basically, material qualification has to go through in these 5 stages. One is at the powder stage, initial thing, then part printing, post processing, material characterization, and mechanical testing. Powder, I have explained what and all we need to check: PhD, morphology, chemistry. Printing, data preparation, slicing, and process parameters. Post processing, stress relieving like supports removal, final heat treatment, solutionizing, haze hardening, hipping, grinding, vibro polishing, all those. And material characterization like density, hardness, sample preparation for porosity and microstructural characterization. Then finally mechanical testing. From powder to end part for application, all those testings we need to perform. This is a simple case study to better understand why additive manufacturing. This is a historic aerospace buy to fly ratios can range from 15 to 30 1 on the high hand, depending on the shape of the part and the manufacturing process. With the implement of additive manufacturing, the wastage can be significantly reduced while also being cost competitive. The different color thing inside, which is the actual component. To produce that, we need to take a workpiece of bigger size and we need to machine it. In this process, to get a 1 kg of final component, we may need to use 15 kgs to 30 kgs of actual raw material. So almost 94% material, some 80 to 90% of material is getting wasted. This can be controlled in using additive manufacturing. Like when you are taking here also, I would like to take 2 minutes break for a discussion. Hello, sir.
Yeah, so you covered many things nicely, Sudarshan Reddy.
Yes, sir.
Questions from audience?
Sir, is there any qualification that we can do to check the dimensions of the parts that are being printed?
Like during the process or after the process, sir?
After the process?
Yes, CMM inspection can be done, right?
Sorry, sir, which inspection, sir? I don't get you.
CMM.
So other than that, is there anything, sir? For example, if I have any internal structure.
Yes, CT scanning can be done, sir, on that, but it's expensive process. Depends on the complexity, how important the dimension needs to be measured. Like blue light scanning is there, CT scanning is there, and like if it is a cooling channel close to the surface, we can go for UT scanning, radiography. There are many techniques, sir, but depends on the what kind of feature you would like to capture. Very fine and accurate we need to capture means then we need to go for CT scan.
Okay, sir. Thank you, sir.
Yes.
Sir, you mentioned about optimization using volumetric energy density. So the parameters that we optimize are machine specific?
No, it's materials specific, and from the mission point of view, which you need to consider is the spot die of the mission, like the laser beam. If it is a mission specific, means if from the mission side, the factor which we need to consider is the spot dia.
Okay, sir.
If spot dia from the mission is taken, remaining all the parameters are material related things. Like when selecting the hatch spacing is nothing but the diameter of the. It will be around like for a given laser spot dia, curing zone is there. Like if the spot size is very high, the laser spot size, the curing zone is also very high. Then the hatch spacing will be selected accordingly. So for selecting and if spot size is bigger, the penetration will be more. So layer thickness also will depends on the spot size. So mission specific is nothing but from the mission side, specifically what we need to take is laser spot dia.
Fine, sir.
Any other questions, sir?
Sudarshan, you mentioned laser welding on this inconel alloy.
Yes, sir.
So how this material behaves under welding?
Yes, it is fine, sir. Like we need to prepare the material. Like we need to do solutionizing before we do the welding, because all the stresses what is produced in the process we need to completely remove it by doing solutionizing. Then by putting proper friction before doing that, the weldability we are doing the qualification of that separately. Like we will print a few bars or different structures and we will laser weld it, and that welded zone make it come in tensile testing, that gauge length and grip length is, the gauge length, we will make that welding zone comes, and we will test it whether that breaking is happening in the welded zone, or it is coming in the part zone. So that level of qualification, if it breaks at the welded zone also no problem, but what is the value? The achieved value is within the material specification or not. And during welding, the welding parameters is also needs to be optimized so that porosity will not get in during the welding process. So for that, like set of specifically it has, we have taken it as a separate project with Magol in Bangalore. They have done a series of laser, like how we are optimizing the process parameters here. They have optimized the process parameters there so that there is no porosity catch up during the welding process, and it is a
Okay, okay, nice.
it is
So
a very
the welding is taking place between AM components or AM versus conventional fabricated in Konalala?
it's AM to AM only, and conventionally also, like for few hybrid things we have done, like one AM aluminum onto different thing, H13 onto additive manufacturing margin steel, like that kind of studies also we have done. For that particular part, its whole component is printed component. So for filler rod also we have printed filler rods in additive manufacturing, and during welding we have used that filler rod to fill the gap.
Okay, okay. So and you have the laser setup, for welding as well.
No, no, sir, we don't have internally. We took the support of Magol lasers. It is in Bommasandra.
Okay, okay.
We have given this project of welding to them, and they have optimized the welding parameters for us to the welding.
Oh, nice. Thank you. And there is one question from audience.
Yes, sir.
In powder printing qualification, what type for qualification we need tensile properties? In general, UTM machine to tensile test, any other procedure to follow on this case?
Question is not clear, sir.
Yes, I understand he's asking about whether
Like
just
when it comes to
interpreting, I'm
when
just
it comes to
interpreting like-
tensile testing, there is no specific testing in additive manufacturing. When it comes to testings, we have to go with normal ASTMs only. Like if it is tensile testing, ASTM E8, it is a standard testing for tensile. The material can be from conventional process, additive manufacturing process, forged, rolling, it can be anything. But when you come to the tensile testing, the procedure for tensile testing is as per ASTM E8.
Yeah.
For the qualification, we have to go with the regular testing procedures. There won't be any specific testings like for tensile in additive manufacturing. It is a different dimension. That won't be there. If it is like that, we can't do comparison between process to process. Is the
Okay.
question and
Yeah,
answer?
yeah. I think no, I think that's what is the question also, I believe. Magibalan, is that I think no, you answered what he asked, I believe. Okay, he said okay.
Okay, sir. Yes, sir.
Yeah, you can proceed now.
Okay.
Darshan. Yes.
Steps involved in qualification. One is material selection. Once material is selected, we need to get the powder as per the composition of the material. Then we need to qualify the powder printing qualification. If we are not using the AM Optomate software, which we have internally developed, then we have to go to the regular DOE method of optimizing the process parameters. Here we need to print the blocks as per DOE, and at every step we need to check density, hardness, and roughness, and we have to like narrow down the DOE so that we will arrive at the final optimization process parameter. Once that is done, then we have to do the product level qualification. This is coupon level qualification. Once coupon level qualification is like for welding, how I mentioned, I directly told we have done the welding, but before that, coupon level qualification of the welding is performed. Once it gave the satisfactory results, then only we have done the welding on the actual component. That is product level qualification. And finally, on the product also, we have done the radiography to see any product porosity is captured in the welded zone. We have kept when if the porosity is there in the welded zone, then we have to perform the welding one more time. That we have done also. Like typical powder manufacturing processes are water atomized, gas, plasma rotating, centrifugal. Typically, gas atomized powders is widely used in this process. Why? I will explain now. Water atomized powders will have a particle size range of 0 to 500 microns. Advantages is high production rate, large PhD, feedstock is in good form. Disadvantages is since it is a water atomized powders, water is using for jetting purpose, so removing water from the powder is a challenge. Irregular particle shape, satellites are present, wide particle size distribution. Gas atomization, you can see how the shape of the powder looks here, very irregular. When it comes to gas atomization, like spherical, sphericity is increased to a bigger extent. And here also we can produce a particle size range of 0 to 500 microns. Wide range of alloys can be produced in this process. Feedstock is in good form. Disadvantages is in this process also there is a chance of few irregular particles that can be produced and wider particle size distribution. When it comes to plasma atomization products, the sphericity, like the quality of the powder, is still improved compared to gas atomization process, but the cost is going high. Plasma rotating electrode process, in this process still you can see how good the powders are looking. It's more the sphericity, the flowability is very good. High purity powders, low productivity. Producing this, if it is gas atomized or water atomized, the throughput is very high. Here it is very less, so the obviously the cost per kg will go high. With centrifugal atomization also, it is the same case. As we go with good quality improvement, then obviously the cost of the powder will go high. In order to compensate, balance all this, like we will select gas atomized powders. The sphericity is okay and the cost is also okay. Like the cost compared to water atomized powders, it is on the higher side, but when it comes to sphericity and suitability, it is preferred to have gas atomized powders. Water atomized powders also can be used in some areas where the mechanical properties are not that important thing. If you take automotive or any stationary component in the automotive sector, their shape is very important, not the strength of the material. In those cases, we can use water atomized powders. That is called general application, general engineering applications. When we go for where money is not the concern, when it comes to space, medical, aerospace, in those areas, money is not the concern. There, the quality is important. There, we can go for plasma atomization powders. The selection of powders also depends on the kind of application. Purely depends on the kind of application. Typically, powder characteristics should be in the range of 15 to 45 microns or 50 to 53 microns. That means, again, if you elaborate it, D10, D50, D90. D10 is nothing but 10% of the particle should have 15 microns plus or minus 3 microns. D50 is nothing but 50% of the particles in a given powder. 50% of the particles should have a particle size of 30 plus or minus 3. D90 means 90% of the particles. Then we need to check the chemical composition as per the normal chemical composition. Shape of the powder should be spherical. Tab density, apparent density, and flowability in order to freely spread the powder on the powder bed. And the phases of the powder as per the material specification. If steel has austenitic phase, has 34 pH, has different phases like that. Whether in the raw material is having the phases which is similar to the actual metal is or not is something which we need to check. And the porosity trap inside the powder should be minimum. And methods to measure particle size distribution. C1 analysis as per the STM 214 is one methodology which will be used for measuring the PST, or laser light diffraction as per ASTM. This is the testing process for tensile, how it is ASTM. For measuring PST, this is some ASTM. This is common across the processes. Whatever is the process we follow, we need to do testing as per the standards to get the result. When it comes to morphology, there are many methods to do it. We were doing using SEM analysis, and the minimum limit if the sphericity is above 0.85, then it is good enough to use the process. Why these PhDs and morphology are very important. You can see when the powder is spread onto the plate, if the wider distribution is there, you can see how the packing is good. There is no pores in the left side image. Where in the right side image, you can see bigger particles and very few smaller particles are there. There is a gaps in between. If the gaps are there, after printing also those gaps will come in the printed component, due to which the powder density will come down. So powder selection is also very important. And chemical composition can be checked using HTME 353 and HTME 1019. And for density measurements also we have standards. Another characterization, if any material in-depth characterization is required after heat treatment, all those, whether you have to do a straight diffraction technique and any EBSD kind of thing we need to perform also, we can perform on the components. The printing of coupons by DOE approach, how the process we need to do to optimize the process parameters. Initially, a set of DOE we need to take, like if here we have taken 16 test blocks with 16 different process parameters, like energy density, whatever we calculate, and the laser absorption factors, whatever we consider, we can't hit bullseye. Like this is the exact value which we need to consider. Nobody can get. We will get the range, like energy density, like 50 to 70 is something which is range we will get. Within that range, we need to formulate the DOE. With the 60 different process parameters that we need to get, and we need to evaluate the properties like density, hardness, porosity. Based on the results, we need to plan the iteration too. Like few parameters are good, means with taking that as reference, we need to split for the DOE 2 with the less number of samples. And in this process, if you optimize it, again, we need to check for density, hardness, porosity, and microstructure. If it is satisfactory, then best parameters we need to pick from that and print for tensile and impact testings. In this test, 3 parameters, and we can see the many tensile and impact coupons are there. And if all the 3 parameters are good, it's not that only one parameter set will work for the given material. There will be many parameter sets which will work for the material. In this case, how the selection will happen is again depends on the productivity. If speed and layer thickness is less, the printing speed will be less. So all those which are based on the productivity and the roughness requirement, the selection of process parameter will be there. And density measurement is as per the Archimedes principle. It is calculated based on the weight in air divided by weight in air minus weight in water. The standard which we follow is HTMP 962. For hardness, if it is a printed coupon, if you directly want to check on the coupon, we will do macro hardness. And if you want to check along the grain boundaries at finer level, then we can do micro hardness. roughness, the printed condition, and after post processing after machine condition can be evaluated as per EN 10049. When it comes to porosity, then we have to use standard material preparation procedure for preparing the sample, like cutting, mounting, polishing. Once that is done, then we have to put the sample into the onto the optical microscope, capture the images, and with the help of images software, we need to evaluate the amount of porosity present in the component. Then comes to optical microstructure. This is optical level. If advanced level EBM, EBST, EDS can also be performed. For us to optimize the process parameter, optical level is a subset enough to get a good amount of confidence in developing the process parameters. When detailed evaluation of the material, detailed qualification of material needs to be performed at the component level, then we need to evaluate EBST, EDAX, X-ray diffraction, all those we need to perform. Here we will etch, depending on the selection of etchant for a given material, we will etch it, and in the image you can see the weld beads. These are along this is a longitudinal direction. Along the build direction, we can see clear weld beads. These are all the penetration, like top weld bead is penetrated into the underneath layer, and there is no lack of fusion. So like everywhere it is present, there is penetrated to the before layer. So finally, good density part achieved. And tensile properties, as per since we have printed like tensile bars in the form of either cubes or cylinders. This we need to measure as per STM E8 for tensile and E23 for impact, and we need to test it. And here the reference like tensile impact, we will go for Wrought-Alike properties. It is very difficult to meet the Wrought-Alike properties. How close the properties are to manufacturing we are achieving compared to the Wrought-Alike. We'll check it if it is satisfactory, and for the given application it is above the specified limit, then it is accepted and taken for the production. Fatigue and creep, normally we will not do it for simple parameter optimization. When there is a specific alloy for a specific application, for a specific component printing, where fatigue and creep is also very important factors to be considered. In those areas, we will take this also into account. Microstructure analysis using SCM, face identification using XRF. This is also pure optional. For the basic level parameter optimization, all these need not to be considered. Once actual component printing, once the qualification step is done, we will be printing actual component. Few customers like HL, BHL, they will ask to destroy the actual component and perform the tensile and impact testing, because whatever we do is a coupon level. But in the actual component, if you pick the tensile coupons and like to get extra confidence, if you see this is the component, in certain sections we will cut it, extract the tensile coupons from this component, and we will test it and qualify it. Very few people where extra level qualification is required. This is the procedure we follow. And CD scanning will be performed to observe porosity, lack of fusion, and cracks. And now I will be showing one case study with the material X22 chrome moly vanadium alloy development. This is for steam turbine blades. This is a DST project in collaboration with the Indian Institute of Science and Triveni Turbines. In this particular DST project, our role is to develop the process parameters and qualify the material for additive manufacturing for printing the turbine blades. The complete characterization of the material is done by Indian Institute of Science by Professor Dipankar Banerjee. The motivation of this material is like normally the turbine blade is made by forging process and by doing the machining of that. In this process, a lot of material wastage is there, And as there are some advantages because of additive manufacturing, because complex shape of features can't be produced through machining, like carbon conformal cooling kind of things can be achieved in additive manufacturing process. So it is always better to have alternate process like additive manufacturing when we change the designs. So this particular material is planned to develop by additive manufacturing process. In this process, we have a spec, that material specification, the chemical composition of conventional method that we have taken. We approached many powder suppliers and finally successfully got the powder with that chemical composition, and we have qualified the powder. Then with the help of our AM Optomet software, we have developed the process parameters, and in a quick run, we have pick the best parameter, then the complete qualification of tensile impact, stress structure, creep testings is performed on this material, and all the properties are satisfactory compared to the conventional methods. And finally, turbine blades have been printed. This is the powder level. We have measured the pH, chemical composition, and morphology. All are satisfactory. Then with AM Optomet approach and without AM Optomet approach, what is the difference using our developed AM Optomet software? Like as I explained, the DOE approach, we have to print many coupons, and we have to go iteration 1, iteration 2, iteration 3, iteration 4, like that. And with the help of AM Optomet, in the iteration 1 at max, iteration 2, within this, with so much of time and money savings, we can develop the process parameters. In the right side graph, you can see number of samples required. With Optomet, with less than 10 samples, we can get the good parameter. Whereas without Optomet, we need to print so many of the test blocks, and the time for developing the process parameter without Optomet is 30 days. If we go with the normal DOE approach, with Optomet, we were able to develop the process parameters within a week's time. And initially with the Optomet, we have taken process parameters for 30 microns and 40 microns, and both we got good density with the porosity levels less than, we got the density 99.95%. And finally we have chosen 40 microns than 30 microns because of productivity. 30 microns will have more number of layers for a given component, so the printing time is less. We are getting similar properties for both the layer thickness. So finally we have taken 40 microns for actual printing, and heat treatments have been optimized. And finally the requirement is tempered Martin set. To achieve that, many heat treatment cycles have been applied, and finally heat treatment cycle is also optimized. This work is carried by Indian Institute of Science. Then comes to mechanical testing. High temperature tensile tests are conducted from 200 degrees to 550 degrees centigrade at 50 degrees centigrade interval time. And graph is plot compared to the conventional. AM properties are superior. In the dotted lines, it is conventional thing is in the line form. You can see the difference. Like all the properties what we got in this process are superior compared to the conventional processes. Then once that qualification is done, then we have printed the actual blades. In the left image also you can see 3 blades which are built vertically. In the right also a few components which we have printed. These components we have printed, and this is checked for 3D scanning inspection for any defects or any distortions compared to the CAD model. With this we have closed this project. With this, I'm closing my presentation, and I'm open for any further discussions.
Thank you, Sudarshan Reddy, for very detailed presentation with beautiful case studies. So now the floor is open for question sessions. Audience, you may please ask your questions.
Good afternoon, sir.
Yes.
Sir, as you discussed about the various powder manufacturing processes like gas atomization and all that, what is the best suited among these, sir?
It depends on application. If cost is also something which we need to consider, then gas atomization powders are suitable. Normally, everybody uses gas atomization powders only when like applications like space, aerospace, and medical, where quality of powder is very much important. Then we can go for plasma atomization. Like for general applications like oil and gas, general engineering, tool and die. In these applications, we can go with gas automation. 90% of the powder production that is used for this process is through gas automation.
Okay, thank you, sir.
There is one question from Prithvi Rajan. Is Opto
Yes.
software is applicable for other DMLS?
DMLS is no other DMLS means DMLS is a single
Yeah,
process.
so yeah, I think I'm understanding is powder bed fusion.
Powder bed fusion process. Other means like other missions other than iFusion. Yes, sir. It is applicable for EOS, SLM,
Yes.
laser tech, additive industries. It is applicable for any mission.
Powder bed fusion machine. There is another question. Cost will be charged based on what basis you will be charging?
For which one, sir?
I think the question I am understanding from Madhi Murugan is that so he's asking about charging for printing.
Yes, that I'll do a few lines like you will be sending the requirement if it is the actual component.
So Madhi Murugan, if that understanding is correct about your question, you can actually directly get in touch with Mr. Sudarshan Reddy, so at their company.
Yes, if you send us the inquiry, we will do feasibility study on that and finalize how much time is required, how much mission time is required for printing those components. Based on how much material gets consumed for that, based on that, we will give the amount. You can write us the inquiry.
So, okay, so just a general question, one question from my side. So let's say to print a 1 stencil coupon from Inconel 718. So what would be the typical charge in terms of rough number?
No, it's not like 1 coupon, 2 coupons. It's like a
for
one
any
time,
print, which cost, let's say about 1 hour.
No, I'll give the example. Like if the component covers complete base plate, then per coupon can come below 500 rupees also.
Okay.
Like if you print only 1 coupon also, we have to run the build, like complete platform, complete powder coating, everything. So when in a given platform, when many coupons are placed, only printing time will get added, not the other time. In the process, printing time is very limited. Like one
so
coupon
more we print in the same bed as well as
same
the
bed,
cost.
the cost will come down.
Yeah, right. So any other questions?
Sir, you mentioned about the AM builder, the INSL file generation. So what all scanning strategies are available in that software, sir?
Right now, only stripe strategy is there, sir. We are implementing chess pattern and a few other scanning strategies for precious metal printing that are yet to implement. Right now, it is running with the stripes pattern.
Okay, sir.
Okay then. So if no other questions, I would like to thank Mr. Sudarshan Reddy for his wonderful speech on metal additive manufacturing. So he started from machine powders, process parameters involved, support structures, and he covered almost all the aspects 360 degree of 3D metal printing. So which I found very useful for the audience. So with this, I thank Mr. Sudarshan Reddy for your wonderful time and talk on this.